All right, hello, Calculus BC. Sorry that I cannot be with you today, but I am with you in spirit, and Mr. Grubel is here to answer any questions that you may have. Today we're going to go ahead and start our 2-week trek through series, all right? So, first of all, I want you to think of the difference between a sequence and a series, okay? A sequence is a pattern, right? We talked about yesterday where the positive integers is the domain, okay? A series is then the sum of that sequence. Okay, so if we have a sequence and we add up all the terms, that is called a series. Okay, notice the notation. You remember this probably from pre-calculus. All right, that sigma means sum. Okay, you remember it, from calculus last year. Okay, k equals 1 to infinity. So this is what we call an infinite series, right? And that's what we are going to focus on, infinite series. Okay. If we have a series that adds up a finite number of terms, then we call that a partial sum. Okay. So above we have an infinite series, and below here we have a partial sum. Okay, so we're going to talk about different ways that an infinite series can converge to a value. Today we're going to talk about, I'm going to call it 3 separate topics, 3 separate kinds of tests to see whether a infinite series can converge or diverge. Remember we talked about yesterday, converging means, in this case, the sum is adding up or approaching to a specific number. Diverging means as we add up our values, they're not adding up to anything. We're either going to diverge towards infinity or negative infinity. Right now we only care about converging or diverging. Sometimes we'll find what we converge to, sometimes we will not. Today will be one of those days where we will find what they converge to. So our first definition, and really I would just write what's down below. If we can find the limit of our sum, then we can say that that infinite sum is that value. Okay? Now notice how this is S sub n and not A sub n. If we can write our sum as a function and calculate its limit, then we know what our infinite sum adds up to be. I will tell you that this is not going to happen very often. We are going to look at a specific case of what we call a telescoping series, and this is what we're going to use to help us figure out if a telescoping series converges and what it converges to. Okay, but if we can write the sum as a function and then take the limit of that sum, then it will give us what our sum actually adds up to be. Okay, so go ahead and write this down. This is a telescoping series. why is it a telescoping series? Let's watch what happens as we plug in 1 and then 2 and then 3. Okay? So if we think about the nth partial sum, okay, that sounds funny, nth partial sum, because we don't know what it is. But if we think about the nth partial sum, then we plug in 1 to get 1 minus 1/2. Then we would add our next term when we plug in 2, 1/2 minus 1/3. And then we would add our next term when we plug in 3, 1/3 minus 1/4. All the way up until, since this is the partial sum, 1 over n minus 1 over n plus 1. Okay. So then what happens? This second part of the first term is canceling out with the first number of the second term. And the second number of the second term is canceling with the first of the third term, etc. And that's going to keep happening until we get to here. Okay? Where basically we are left for our partial sum with the very first number of the first term and the second number of our last term. Okay? So here's our nth partial sum. Flash back to this previous slide. If we can take the limit of this nth partial sum, that will give us what we converge to. Okay? So, if we take the limit as n approaches infinity of 1 minus 1 over n plus 1, if we have 1 over n plus 1 as we go to infinity, we know that that is going to go to 0. So our limit is 1. What this is saying, since this is finite, we're converging. More specifically, we know that the sum of k equals 1 to infinity of 1 over k minus 1 over k plus 1, we know that it converges to the value of 1. We know that that sum equals 1. Okay, so you can even write it like this. You can say it converges to 1. We know that it equals 1 is essentially what that means. Okay, but we're going to write it converges to 1. Okay, now, this method of finding the nth partial sum and taking the limit, that's not going to work out for us very often. You see that this is a special case because all of those terms in between cancel out, and we can write our nth partial sum as just a couple of terms with n and then take the limit. But this is only going to happen in a specific case. Here we have the telescoping series. That's the only time you're going to see it able to happen. Okay. All right. Let's talk about a series you do know something about. In pre-calculus and in Algebra 2, you talked about the infinite geometric series. Go ahead and write this down. So, sometimes this function this series converges. Sometimes this series will diverge. How do we know which one? Okay. If the absolute value of r is between 0 and 1, then that series will converge. And we're going to be able to figure out what it converges to. If the absolute value of r is bigger than or equal to 1, then that series will diverge. Okay? If you remember back to We kind of talked about this yesterday, okay? But a geometric series is when you have a sequence where from term to term you are multiplying by the same number. So I think yesterday we had the sequence 1, 1/3, 1/9, 1/27, etc. Okay, this is a geometric sequence where we're multiplying by 1/3 every time. Okay. Now, if you remember, back in pre-calculus, we can actually figure out what this converges to. Okay. If our R value, the number that we're multiplying by from term to term, is the absolute value between 0 and 1, then our sum will be the first term over 1 minus R. I am going to make a note right here that this is the first term. There could be some tricky cases where the first term is maybe when our series starts at 2, and we'll talk more about that on Monday, but make sure that that A is the first term no matter what your series is beginning at. Also, if you flash back to pre-calculus, if we want a partial sum, the partial sum of an infinite geometric, or the partial sum of a geometric series is the first term times 1 minus R to whatever partial sum you're finding over 1 minus R. We will not use that very often, but just so you have that to reference, this is how you would find a partial sum. Okay, so let's go back to that sequence I was talking about earlier. Yesterday you had 1, 1/3, 1/9, 1/27, etc. If we change this to a series, then this would be the series, n equals 0 to infinity. Our first term is 1 times our R value is 1/3, since that's what we keep multiplying by. Okay. So we're going to write it like this. Okay. Now, I know yesterday we did this for starting at 1. Geometric series will typically start at 0. Okay, so this rule looks different than what we wrote down yesterday. These will be the only series that are going to start at 0. The rest of them are going to start at 1. Okay. So if we wanted to figure out where this converges to, we take the first term over 1 minus that common ratio. This infinite series converges to 3/2. If we add up all of the terms all the way to infinity, our sum converges to 3/2. Let's look at this one. So you can see that from term to term, we multiply by 2/5. Okay? So we can write that this is the sum from 0 to infinity. Our first term is 3, and then 2/5 is that number that we keep multiplying by from term to term. Since 2/5 is less than 1, we know that this series will converge. To find what it converges to, we're going to put the first term over 1 minus r. We know that this series converges to 5. Now, eventually, you're going to have to give a reason for every single series why it converges and why it doesn't. So let's start that now. This converges to 5 because it is a geometric series where the absolute value of r is between 0 and 1. We're eventually going to get a lot of these series tests, and you're going to have to back up why a series converges or diverges. So you're going to have to tell me how you know that it does or not. So we know that this converges because it's geometric and the r is between 0 and 1. Additionally, we know it converges to 5. Okay. Next test that I want to talk about is what we call the nth term test. And this is going to be something that you are going to always think about first. Okay, because if it doesn't pass the nth term test, then there's no point of moving forward. Okay? So this is saying if a series converges, then the limit of the sequence must be 0. Okay. Now, that's actually not what is helpful. Okay. What's going to be helpful to us is the contrapositive. The contrapositive, if the limit as n approaches infinity of our sequence is not 0, then our series does not converge, which we call that divergence. Okay, so we took this sentence, we flipped it around and negated both pieces of it. Okay, so we took if B then A, we took if A then B and wrote if not B then not A. Okay, so if the limit is not 0, then the series diverges. That is what you are going to think about first. You are going to look at the limit of your sequence. If it's not 0, then automatically we know that it diverges and we're done. If it is 0, then we can consider other tests. Okay, right now we have the telescoping series and we have the geometric series. So, not much to go off of right now, but once we get into, more of these tests, we'll have more of a fallback. But this is the first one that we need to decide. Is the limit 0? If it's not, it diverges, end of story. Okay. So I have 3 examples here. Right now, we don't have very much knowledge about tests of series. Right now, we have the nth term test, we have the geometric series test, and then we have the telescoping series. This is not a telescoping series, okay? The telescoping series will be disguised as a fraction minus another fraction, okay? So, obviously this is not geometric. What we need to consider, and what I said on the previous slide, let's always think about the limit towards infinity first of the sequence, and then we can go from there. So let's consider the limit as n approaches infinity of our sequence. Okay, some of you are panicking. Oh my goodness, how do we find this limit? Okay, do not worry. My suggestion would be to think of dividing both the numerator and denominator by n factorial. Okay. So basically we would have 1 over 3 plus 2 over n factorial. Okay? If we think about the limit towards infinity, this 2 over n factorial is obviously going to go to 0. So we're left with 1/3. We just took the limit of the sequence. It is not 0. I don't have enough room to write that. Sorry. So, what you're going to write is that this series, diverges because of the nth term test. And you're going to show me that you found the limit to not be 0. Okay, so we found the limit. It's not 0. So then we write it diverges by the nth term test. I need to see all of that work. Next. Okay. So, I'm hoping that you can recognize that this is a geometric series. Anytime we have a constant raised to a power, I want you to be able to recognize that that is geometric. Okay? Now, what do you notice about R? The absolute value of R is greater than 1, right? So, what I would need you to write is that this series diverges because it is a geometric series where the absolute value of R is greater than 1. That would be what I need. Okay? You can't simply write diverges. I want to know why you think it diverges, or how you know it diverges. Okay? You could use the nth term test on this one, and that would be fine. The limit towards infinity of 3 to the n is not going to be 0. So if you wanted to go that route, you could, but I'm hoping that you can recognize this as a geometric series. Okay, last example. Okay. So the first thing I want to consider is the limit of our sequence. The limit of our sequence is 0. That is a good thing, but that doesn't tell us anything. Okay? If it wasn't 0, we would know for sure that it would diverge. If the limit is 0, that theorem tells us nothing. The nth term test is not helpful here. Okay? This is not a geometric series either, so we cannot use that rule. And our telescoping series is not going to be helpful either. Okay? This is a series that we're going to have to wait until next week to figure out if it diverges or converges. I'm sorry to disappoint you. But what I want you to understand is that if you try the nth term test and the limit does equal 0, you don't know anything. Okay? This series could converge, but it also could diverge. The only thing we know for certain is if we take the limit of the sequence and it is not 0, then it diverges. That's the only thing that we can use that theorem for. If the limit is 0, we've really gotten nowhere. All right? So if you have any questions, ask Mr. Greenwell. And then what I'd like you to do is begin working on your assignment, which you can find on your gold sheet. And we will see you on Monday.